Hello, friends. Today we are going to study about the torque. Is torque, and thereby we will study about the starting torque of three-phase induction motor. Because we have been three-phase induction motor in the classroom. So we first of all go through the basic. What is torque? Thereby we will go for the starting torque, which is being developed by the three-phase induction motor or which is developed by the three-phase induction. So, what is torque? Torque is defined as a product of the force and distance, which is measured in the Newton meter. If we formulate the torque, so torque will be formulated by this way. Torque is defined as I have already defined it, torque is defined as a product of the force and distance covered by the mass or distance, which is measured in Newton meters. So how do we measure the torque? So we have already studied one formula or derivation for that formula, that power P equals to N, means revolution per minute or revolution per second, which will be based on the N by 60, N 2 pi means one revolution, T. Right now N is in the revolution per minute, so it will be converted into the second, so divided by 60. Okay, so this is the basic formula what we have already studied. But from this formula we can also derive the torque. So torque is made as a subject, so T equals to P into 60 divided by 2 pi N. So this is the formula for defining the torque in fundamental way or by the fundamental way. But we are going to derive the torque equation with the help of electrical parameters, because of we are studying three-phase induction motor from electrical point of view. So we will just consider the parameters which are associated to develop the torque in three-phase induction motor. So the total torque produced at the outer periphery of the shaft will be defined by the certain parameters. So that torque is known as a starting torque, what we are going to study. But there are various kind of torques, what we will study when we will study about the torque and slip characteristic. So what are the types of torque we will also see over there. But right now we will just see basic types of the torque. So types of the torque. Types of the torque. So first is starting torque. starting torque. Second one is pull-up torque. Pull up torque. And third one is breakdown torque. Break down torque. And fourth one is full load torque, or it is also called as a operating or rated torque. Full torque. So there are these kind of torques which have been mentioned here: starting torque, pull-up torque, breakdown torque, full load torque. So these are various kind of torques which are produced by the motor on the outer periphery of the shaft. So we will study the starting torque because of starting torque is most significant torque because of each and every motor has to overcome from its own inertia as well as the load or other machines connected or coupled with it. So machine has to overcome or lift both load as a load connected to the machine and its own inertia. So it will have to produce optimum power or optimum torque at the time of starting. So starting torque must be higher than the operating torque. So we will go to study first of all starting torque. What is starting torque and how do we derive it with the help of electrical parameters? And what are the parameters which significantly affect on it? And what are the parameters by which we can control the torque at the time of starting? So let us go through the starting torque. We will study the starting torque produced by three-phase induction motor. So we go for that. For point, starting torque Starting torque produced by three-phase induction motor. So to understand starting torque, we need to first of all classify the circuit. So there are basically two circuits in this three-phase induction motor. First one is a stator circuit, second one is a rotor circuit. And there is a air gap between stator circuit and rotor circuit. So I will classify both circuit as a circuit 1 or circuit 2. So circuit 1 will be considered as a circuit 1. Circuit 1 is equal to a stator circuit. Stator circuit. So we will also see the some parameters associated with the stator circuit. But three-phase induction motor is a three-phase system or three-phase machine. So we will consider it for the per phase system. Means we will denote all the parameters with respect to the per phase system. We will not denote or we will not represent any of parameters with the three phase or by the three phase system. So let us represent what are the parameters. So first one is a E1, which is the supply voltage of the stator winding. So supply, I write it in the short form, supply voltage to stator. I1 means current of stator winding. Stator winding. Current of stator winding. Z1 impedance of stator circuit. So we have mentioned three parameters: E1 supply voltage to the stator winding, I1 current of a stator winding, Z1 impedance of stator winding. All three parameters are associated with the stator circuit, but those are considered, or we have to consider those parameters as per per phase or per unit system. Per phase system or per unit system. I have not represented it by the three-phase system. This is for the circuit 1. Let us go for the circuit 2. Circuit 2, which is equivalent to the rotor circuit. Rotor circuit. So now we will see all parameters associated with the rotor circuit. So first one is a E2. So E2 equals to the rotor EMF induced EMF induced EMF induced in rotor. Rotor circuit. EMF induced in the rotor circuit. Second, current I2. So EMF induced in rotor circuit, due to the EMF, there will flow the current I2 in rotor circuit because of rotor circuit is shorted by end rings or slip rings. So current in rotor circuit. E2, I2. Similarly, there will also be the impedance in this rotor circuit. So that is also represented by the impedance in the rotor circuit. Impedance in rotor circuit. So we have also seen the parameters of the rotor circuit, which consist of E2, EMF induced in the rotor circuit. We do not give any supply. EMF is induced in the rotor circuit by the Faraday's law. So if EMF is induced in the rotor circuit, so there will also flow the current when circuit is short circuited or circuit is closed. So circuit is short circuited in both squirrel cage rotor and slip ring rotor by the end rings and slip rings respectively. Z2 impedance of the rotor circuit, which consists of Z2 consists of resistance of rotor circuit R2 square plus R2 square plus X2 square means inductive reactance of the rotor circuit. X2 square. So that is our Z2. Z2 is the resultant of R2 square plus X2 square in the rotor circuit. Now we will see how does a starting torque produce and what is the basic equation or derivations for the starting torque. So as we know that torque is produced at the outer periphery of the shaft, or torque is produced at the shaft. So force is applied on the shaft which rotates in the angular motion. So why does force produce? Because of force produces due to the interaction of magnetic flux produced by the stator circuit and magnetic flux produced by the rotor circuit. If there will not be produced the flux due to the rotor circuit, so it will not interact with the flux of the stator circuit, so there will not produce any kind of force. So to produce the force or to produce the torque, rotor circuit parameters are most important and most significant. Because of, as we know, the basic principle of the three-phase induction motor. So what is mentioned over there, whenever we give the three-phase supply to the stator winding, it produces the rotating magnetic field in the air gap, and this rotating magnetic field is a rotational, or it can be said that it changes at every moment because of it is a rotational magnetic field. So there are conductors in the rotor. Rotor conductors are cut by the magnetic lines. So due to the rate of change of flux linkages, there produces an EMF in the rotor conductor, and those rotor conductors are shorted by either slip ring or end rings in squirrel cage. So there flows the current, and this rotor current produces its own magnetic field in the air gap, and this magnetic field of the rotor circuit collides or interacts with the magnetic field of a stator circuit, which results into the development of force, and that force transfers on the rotor, and shaft or entire assembly of rotor rotates. So if there will not be produced current in rotor circuit, it will not produce the flux. So torque will not be developed. So rotor circuit parameters are most significant parameters which assist to develop the magnetic force and which produces the torque. So rotor circuit parameters only assist to develop the torque. So our basic equation is starting torque torque will be denoted by TST. What is that? We will denote the starting torque by the TST. So rotor circuit parameters assist to develop the torque. So value of the torque, variation over the range of torque, intensity of the torque, level of the torque only depend upon the parameters of the rotor circuit. So we will represent starting torque by the parameters of the rotor circuit. So TST is starting torque. starting torque is proportional to what? So we will see. We know that basic formula for the torque is what? Basic formula for torque is phi into I. Flux into I, what we have already studied in the DC machine or DC motor. So here it is also same. Torque produced by any of AC machine will also follow same formula, but there is just difference of that was a DC quantity, here it is a AC quantity. So one additional parameter will be added, but torque is proportional to flux phi, current I2, flux phi. This is the flux which is produced by the stator winding. So this is represented as a phi. Second, I2, we can also write it as a phi 2, but that phi 2 or a rotor circuit magnetic field has been produced by the current I2, so that we have not written it as a phi 2. We write directly I2 because of phi 2 has been produced due. So flux phi and I2, and starting torque is proportional to the flux phi and current I2, but both are dependent on AC quantity. So there will also be the phasor differences, cosine angle between the voltage vector and current vector of the rotor circuit. So there will also be effect of this parameter. So cosine angle will be written as a cos phi. So starting torque is proportional to the flux phi, which is rotating magnetic field produced by stator winding. I2, current of rotor circuit, and this current contributes to produce the flux of rotor circuit, and there will also be the cosine angle between voltage vector and current vector in the rotor circuit. So that has also been represented as a cos phi 2. Hence rotor circuit power factor. So phi will be as it is, but current I2 will be written as a, what is the basic formula of I? I equals to V by R, but here it is AC circuit, so there will be Z. So I2 equals to E2, induced EMF in the rotor circuit, E2 by Z2. As we see here, there are three parameters in the rotor circuit. Z2, which is the resultant of R2 square plus X2 square. And second, E2, means when induced EMF will produce in rotor circuit, thereby current will flow. So current has been produced by the formula of E2 by Z2. So I2 equals to E2 by Z2. Okay, next, cos phi 2, which is power factor. So what do we write to power factor? Cos phi 2. This is the power factor of rotor circuit. So it can be written as R2 by Z2. Let me write it as R2 by Z2, means power factor of the rotor circuit. So these two conditions have been obtained from the circuit 2. Power factor formula, you know that cos phi 2 equals to R2 by Z2, I2 equals to E2 by Z2. and these two value will be placed in the equation, this starting torque equation. So let us go ahead. TST, starting torque, is proportional to phi into I, which has been written as a flux phi I2 of rotor circuit, cos phi 2 of the rotor circuit. Now place these two I2 and cos phi 2 value into the equation of TST. So let us go to keep the equation, the value of I2 and cos phi 2 in this equation. So it will be written as TST is proportional to flux phi as it is. I2 equals to E2 by Z2. E2 by Z2. And cos phi 2 equals to R2 by Z2. So now we will simplify this. TST is proportional to the flux as it is. I2 has been replaced by the E2 by Z2. Cos phi 2 has been replaced by the R2 by Z2. Now we will remove the proportionality. As we know that whenever we remove or eliminate the proportionality sign, so there will come the any constant. So that constant will be considered as a K. So in the next step, TST equals to, here proportionality sign will be eliminated. So proportionality sign will be eliminated. So it will be K flux phi as it is. Flux phi will be written. Flux phi next E2. E2 and R2 will be written as a combined E2 R2. R2 square. Then divide by Z2 square. So K phi E2 R2. All numerator value have been placed as it is. There is no changes. By default, there is a by mistake. There has come R2, only R2. Okay. Divide by Z2 all square. Because of there is Z2, E2 by Z2, R2 by Z2. So I have multiplied both the values and we have taken the equation like this. So now we will simplify it. So TST equals to A flux phi E2 R2 E2 and R2 divide by Z2. What is value of Z2? Z2 is equals to under root all. We will place the value of Z2. So what is value of Z2? As we have sent Z2 equals to under root R2 square plus X2 square. Okay, so R2 square plus X2 square whole under root. So that will be written here. R2 square R2 square plus X 2 X2 square whole square because of Z equals to Z2 equals to under root R2 square plus X2 square whole under root. So here we will write same thing, and whole under root R2 square plus X2 square, but there is a square Z2 square, so that square and under root will be cancelled. So when under root and square will be cancelled, so there will be remaining this equation. TST equals to K plus phi E2 R2 all divided by R2 square plus X2 square. Okay, so this is your formula for starting torque, which is dependent upon the flux of flux produced by the stator winding, induced EMF in the rotor circuit E2, rotor circuit resistance, whole divided by R2 square, means square of the rotor circuit resistance, square of the rotor circuit reactance in the denominator. So this is the formula of starting torque, what we were searching. So this can be denoted as a equation number 1. So this is our formula for deriving the starting. This is our formula of starting torque for three-phase induction motor. And there are those parameters which contribute to develop the starting torque. But this is the starting torque formula, which does not represent the maximum value. As we have already mentioned earlier, that motor or machine has to start with its own inertia along with the load or burden coupled to it. So it requires the maximum force or torque to be developed at the time of starting. So we need to define the maximum torque. So when will we get the maximum torque, and at which condition will we get the maximum torque? So maximum torque condition can be satisfied with some variable parameters. So we need to find here some variable parameters with the help of which we can differentiate this equation, and by differentiating this equation we can get the condition for the maximum torque. And after getting the condition of maximum torque, we will place that condition in this equation number 1. So what is the variable parameter we need to define from this equation? So flux is constant because of supply voltage is constant. Induced EMF will be constant because of flux is constant. So phi and E2 will not vary. Reactance at the time of starting will be constant. So what will be variable? Variable will be your resistance. So here we will consider R2 as a variable in this torque equation of the starting condition. So this equation number 1 will be differentiated with respect to R2 because of we have considered R2 as the variable parameter. So let us do that. We differentiate this entire equation with the help of R2. So d dst entire equation means dst all divided by dst by d r2 dr2 equals to 0. Means this whole equation will be differentiated with respect to the k phi e2 by r2 whole upon r2 square plus x2 square. Means this whole equation will be differentiated with respect to r2. So let us do with that. So as we know that whenever there are such a conditions, so we will keep numerator value, denominator value will be kept as it is and differentiation of the numerator value. Right? R2 square plus x2 square R2 square plus x2 square all square, sorry, into d by dt or d by dr2 of which equation is numerator value. Denominator value will be as it is, numerator value will be differentiated. So k phi e2 r2. K phi e2 r2. Okay. Now minus, first of all, we have differentiated numerator value. Now denominator value will be differentiated and numerator value will be kept as it is. So what will be k k phi e2 r2. This is numerator value. K phi e2 r2 is the numerator value which is kept as it is, and denominator value means r2 square plus x2 square will be differentiated. So let us differentiate it. D by dr2, d by dr2 equals to r2 square plus x2 square all divided by numerator values whole square will be. So let me keep r2 square plus x2 square whole square equals to 0. It means we have differentiated TST, starting torque equation, with respect to the R2. So dTST divided by dr2 equals to 0. We have differentiated this entire We have placed the equations as per differentiations conditions. Now we will differentiate it. So what will be R2 square plus X2 square as it is? R2 square plus X2 square will be as it is. Differentiation of this term means R2 equals to 1. So this will be written as a phi B2 and R2 is differentiated. So it is as a 1 minus K phi E2 R2. This value will be as it is. K phi E2 R2. K phi E2 R2 will be as it is. We will differentiate only R2 square because of X2 square is not associated with the R2. There is no any term associated with X2 pertain to R2. So R2 is not associated with the X2 square, so it will be considered 0. So we will just differentiate the R2 square. So it will be written as a 2 R2. All equation divided by this. And if this denominator value R2 square plus X2 square whole square will be multiplied with the 0, so it will be 0. So we will neglect it. Okay, if this will be multiply with this, so it will be 0. So we will not write this in the next step. Now, what will be this term which are in minus will be shifted on the right hand side. So what will be? It will be written like this. R2 square plus X2 square K phi E2 K plus phi E2 equals to, this term will be shifted on the right hand side. So K plus phi E2 K flux phi E2. R2 into R2, R2 square. So it will be written as a 2 R2 square. 2 R2 square. Okay, R2 will be multiplied. So on the left hand side, R2 square plus X2 square, K phi E2, 1 will be multiplied with it. So it will be as it is. On the right hand side, K phi E2, R2 will be multiplied. So R2 square. So here it will be cancelled. K phi E2 will be cancelled. So when you will cancel these two terms, these three terms on both sides, so what will be? R2 square R2 square plus X2 square equals to equals to 2R2 square. There is 2R2 square. R2 square plus X2 square equals to 2R2 square. These two terms have been cancelled on both the sides. So R2 square will be shifted on this side. So what it will be minus. So X2 square equals to 2R2 square minus R2 square. So it can be written as a X2 square equals to 2R2 square minus R2 square will be only R2 square. If we will eliminate or drop out square on both the sides, so what would it be? It will be X2 equals to X2 equals to R2. So X2 equals to R2 is the condition for getting the maximum torque as an output. The maximum torque will be developed by the any of machine or motor when there will be the resistance R2 of rotor circuit is equivalent to the inductive reactance X2 of the rotor circuit. So this is the basic condition of getting the maximum torque. X2 equals to R2. So now we will place this condition for maximum torque. Condition for getting maximum torque. Condition for getting maximum torque. So put this condition in the equation 1. Let's put this condition in equation 1. Let us place this condition let us place this condition in equation 1. So this condition will be placed in our this equation TST. Wherever there are R2, we will replace it by the X2, and where are there are X2, we will replace it by the R2. So we will keep both the conditions. So let us see. Put put R2 equals to X2 in equation put R2 equals to X2 in equation 1. So now we have defined the condition for the maximum torque. This is the condition for maximum torque, which is X2 equals to R2. So now we will change the entitlement or name of TST. Now we will write it as a maximum starting torque. So TMST. So TMST equals to TMST equals to this formula K phi E2R2 K plus phi E2 R2. Okay, so we have kept the condition wherever there is R2, we will replace it by X2. R2 equals to X2. So there is R2 in the numerator, so that R2 will be replaced by X2. So let me replace it by the X2. At the denominator, R2 square will be replaced by X2 square and X2 will be as it is. So R2 square will be written as a X2 square plus X2 square will be as it is. So now this will be written as a K plus phi P2 X2 all divided by 2x2 square. So 2x2 square. So x2 will be cancelled by x2 square. So what will be? There will be only formula TMST TMST equals to K plus phi E2 all divided by 2x2. So this is the formula for maximum torque. This is considered as a equation 2. This is our condition for the maximum torque. Maximum torque will be available when R2 is equals to X2. So in this case, we have replaced R2 by X2. In the next equation or in the next condition, X2 will be replaced by R2. So what happens when we replace R2 by X2? So put X2 equals to R2 in equation one. Okay, so we will write it as a TMST because of it is maximum torque. TMST equals to K phi E2 K flux phi E2 X2 will be replaced by R2. So our formula is K phi E2 R2. R2 will be as it is, just the denominator value X2 square will be replaced. So K phi E2 R2 will be as it is, all divided by R2 square plus X2 will be replaced by R2 square. Now this will be written as K flux phi E2 R2 all divided by R2 square plus R2 square. 2 R2 square. So now here R2 will be cancelled by R2 square. So our equation will be T m maximum starting torque equals to K flux phi E2 K flux phi E2 divided by 2 R2. So this is our formula 3. Which is similar to the formula number 2, TMST and TMST, K phi E2 by 2 R2, K phi E2 by 2 X2. It means if we replace R2 by X2, so condition will be same. And if we replace X2 by R2, so condition will be same. So maximum torque in any condition will be achieved when R2 is equal to the X2 in rotor circuit. So we have derived the formulas for the maximum starting torque under the condition of R2 is equal to the X2, and we have derived the formula for the starting or normal or general starting torque. So general starting torque formula is represented by the TST equals to K 5 flux 5 induced EMF E2 in rotor circuit, rotor resistance R2 all divided by impedance of the rotor circuit, means R2 square plus X2 square. And this equation has been differentiated with respect to the variable parameter R2, which has been considered by us. And then have got the condition X2 is equivalent to R2, and this condition X2 equals to R2 has been placed in our first equation, and we have simplified it. So we have got the maximum torque, maximum starting torque formula, or by which we can derive or calculate the maximum starting torque produced by the motor, means maximum torque produced at the time of starting. So the formula for maximum starting torque is same in both the conditions when R2 is replaced by X2. So in the denominator, 2X2 will come when X2 will be replaced by the R2. So in denominator, 2R2 will come. So by this way, we can calculate the maximum torque produced by any three-phase induction motor at the time of starting by these three formulas. And these formulas will be used or utilized to calculate the torque in the numerical way. So that's all over here. We will discuss in the next lecture about the calculation. Thank you.